This is Bill Johnson. I'm working with Eddie Pazmiño to make videos to explain Parti-Suite software. This video concerns detachment. But to get to detachment, we have to explain attachment. And so in this video, I'm going to run a quick loading simulation and then use perturbations in either ionic strength or flow to try to detach those attached colloids. And so in this loading simulation, what I'm going to do is set this for just 4 colloids in contact mode rather than perfect sync. And superficial velocity of 1.62 times 10 to the minus 6 meters per second. I'm going to use an injection radius of 10 microns, 100 microns. In a Happel sphere with a porosity of 35%, a grain radius of 510 microns. The colloid radius is going to be 10 microns. The density corresponds to polystyrene. Fluid density parameters are typical. I'm going to add heterogeneity to the collector surface because I know that before I go to the heterogeneity, I'll go over here to the mean field zeta potentials. And so I'm going to have an ionic strength of 20 millimolar, a monovalent electrolyte like sodium chloride, a collector zeta potential of minus 25 millivolts, and a colloid zeta potential of minus 25 millivolts, which is reasonable for carboxylate modified polystyrene latex at 20 millimolar and a pH around 8. The colloid heterogeneity parameters then, or actually collector heterogeneity parameter, I'm going to set at 450 nanometers for the radius of the heterodomains on the collector. I'm just going to have one size, and they're going to be charged positive 25. I'm not going to put colloid heterogeneity on here. I'm going to keep it simple for now. The van der Waals force parameters correspond to polystyrene latex interacting with glass across water. Roughness, I'm going to set to 50 nanometer asperities that set the colloid collector interactions. They're going to be on both surfaces. And then larger asperities of 500 nanometers are going to set the hydrodynamic slip length. All that's explained in Rasmussen et al. 2019, if you're interested. And then the Lewis acid base, steric, and deformation parameters all correspond to polystyrene latex interacting with glass across water. Those are all explained in Van Ness et al. 2019, if you're interested. I'm going to use a bulk time multiplier of about 30, a near surface time multiplier of 4, and a contact time multiplier of 0.2. And then the ratios relative to diffusion for displacement in the near surface. So if the displacement is less than 1,000th of diffusion in the near surface, I'm going to consider it stationary, not arrested, because it's in the near surface, not in contact. But I don't. If it gets around to the rear flow stagnation zone, I don't want to sit there forever computing it. We're going to use that factor of 1,000th to call it done. Likewise, in contact, if it's rolling across the surface at a rate that's less than 10% of the displacement one would expect from diffusion in bulk fluid, then we're going to call it arrested. So we don't watch it roll slowly forever. So those are my parameters. I'm going to go ahead and start the loading simulation. As I do that, the dashboard figure shown here, I'll maximize this. What you can see here is that the colloid enters the system at within some radius that we had specified. I said 100 microns from the forward flow stagnation zone. Locations are chosen randomly within that radius. This colloid is moving rapidly towards the surface. It has a significant settling, and that's probably why. It's now within 200 nanometers of the surface. You just saw that near surface plot that's initiated within 200 nanometers of the surface. You can see that the zone of interaction between the colloid and the surface here in the bottom right was significantly filled by heterodomains. It went over a heterodomain, but it did so when it was too far from the surface to actually go into contact. Now, here's another near surface plot. Next time I see one of those, I'll maximize it so you can see what's going on. But the point is, it is going over heterodomains, but it's still too far off the deck to attach. So now it's within several tens of nanometers, about 30 nanometers from the surface. It is now going over another header domain. You can see the zone of interaction is occupied now 20% by a header domain. We'll see if it will increase further. It could come into contact if it does. Just to show you a bit about the near surface, the equatorial ring of the colloid is projected onto the collector surface from a map view. The header domains, a limited number of them, are shown within that projection, and then the zone of interaction of the colloid is shown. And you can see it's overlapping one of these header domains. A side view shows the same thing. You can see the radius of curvature of the collector. These images are much more interesting when you have heterogeneity on the colloid and the collector. They're very informative that way. So it is now firmly in the secondary minimum, approximately appears to be somewhere between 10 and 20 nanometers from the surface. It has moved past that header domain, so it went over part of that header domain. It didn't go directly over it. And as the tangential velocity moves it across the surface here, it will cross additional header domains, which will become clearer in the near surface plot. Now it's going over another one, and it's achieving at this point almost 40% coverage. That's enough to bring it into contact. You see the dots turn blue in the trajectory, and now the contact plot in the upper right kicks in. So the adhesive contact force, which includes van der Waals, in this case, Lewis acid base, and electric double layer now that it's over a positively charged heterodomain. Those are all adhesive forces. The repulsive forces include Born as well as steric. And what will happen is that the colloid will come into an equilibrium separation distance from the surface that balances these forces. It will be snug up against the steric and Born repulsive forces. Once it reaches that equilibrium separation distance, the torque balance will determine whether it stops rolling. And the torque balance is set by the adhesive forces multiplied by the contact radius, as set by deformation of the colloid. And the driving torque, the mobilizing torque, is set by the fluid drag multiplied by the lever arm defined by the distance slightly more than the radius of the colloid, set by the deformation of the colloid, the leading edge of that deformation radius up into the center of the colloid. So it's been an hour since the last time I've checked in about this coming into contact, and this is, of course, is a painfully slow approach because we know it's going to arrest by experience under these conditions. And what's happening is that probably our output interval up here in the top center is too low, and so it's spending a lot of time plotting these data points. The other possibility is that the contact multiplier is too low, can be raised to 1, or likewise the contact displacement factor can be changed so that arrest is recognized as a higher fraction of the displacement expected from diffusion. So those things are adjustable. Well, this thing hasn't fully finished resolving in that it's resolved, but it hasn't given me the continue button, which will come on in just a sec. But this is a colloid. This is one of those colloids that has quote unquote attached, in that it introduced into the fluid envelope here, came down at the surface, there's the continue, went into contact, and then slowly rolled into a rest. But that arrest, as shown by this magenta dot, they're blue dots when they come to a complete arrest. But because I chose a contact displacement factor of 0.1, once it reached 10% of the displacement that diffusion bulk solution would cause, that was considered effectively arrested. And so that was given an attach K value, shown here in the GUI, of 4. And given the injection radius we used, that equates to an eta of 0.11. Now, we would have to vary the injection radius in order to get a more accurate eta. but that's covered in another lecture. The point I want to make here is that we can look at the contact rendering and actually move that around, because the collector surface is shown here, the colloid surface in the red, the colloid surface is shown in the gold. Those are the unfavorable colors. And those hemispheric bumps represent the roughness, which for the colloid collector interactions are set at 50 nanometers. The 500 nanometer roughness that was set in the simulation represents the hydrodynamic slip. Those aren't represented here. And so the conceptual way to consider this is that the 50 nanometer asperities are superimposed on the 500 nanometer asperities. So this is a somewhat non-physical representation, but it's a reminder that that roughness exists. And if we rotate this, we can actually check out, how this thing attached. So I'm looking now from the collector surface side, and you can see that the projection of the zone of interaction is shown in this gold ring, and the heterodomain fills the majority of that zone of interaction. And that's what's responsible for the net attractive interaction that allowed colloid to attach. Don't get confused how in the near surface figures, the more obvious ring is the equator of the colloid, but in the contact figure, this gold ring is the zone of interaction. The equator of the colloid is far outside the view of this image. And if we look on the colloid side of things, there was no heterogeneity on the colloid, so we're looking through the colloid to see the heterogeneity on the collector surface. Okay. Whereas if we had heterogeneity in the colloid, we would see that as well, and that can act complementarily with the heterogeneity on the collector to allow attachment. And that's described in a very recent article, in fact, just published in the past couple of days by Cesar Ron in Environmental Science Nano 2020. I think that's enough on this contact. So this one's taking a little while to resolve, even though I've got the provisional attachment, displacement factor for contact set at 0.1. And that's because the heterodomain is filling the entire zone of influence, which means there's a very strong attraction. That's why the attractive forces, the adhesive forces were very high, going up to almost a nanonewton. And sometimes I see these attached with piconewton attraction, but it's almost a nanonewton, and the repulsive forces are catching up. It's really snugging up against the surface, and that's why there's some additional trajectory points down here, very close to a few newtons. So the ultimate separation distance for this one's going to be smaller, like a few nanometers as opposed to 5 nanometers, for example. And that's how you get a range of ultimate separation distances based on how much attraction there is, which is based on how much the heterodomain fills the ZOI, as well as other things like the zeta potential of the heterodomain and ionic strength and other things that control the interaction forces. So another colloid, actually 4 out of 4 colloids introduced into this system attached, and here's a contact plot for another one of them, and you can see again there's the colloid surface in gold, showing the smaller radius of curvature. We're looking now from below the collector surface in red with the larger radius of curvature, and the zone of influence between the colloid and the surface shown in the gold ring, and the overlap of the heterodomain shown within or around the gold ring, but also partially within. And notice this is a smaller overlap. This colloid in the trajectory came into contact with this heterodomain while it was very close to the surface, about 10 nanometers from the surface, and so it attached as soon as the fraction of the ZOI was large enough to allow it to attach. Others landed or came into very close contact within 10 nanometers when they were right over the top of the heterodomain, and they had almost 100% coverage. So that's how you end up with also differing fractions of the ZOI occupied by a heterodomain, which gives them different tendencies to detach in response to increased fluid velocity and decreased ionic strength. It also gives them different equilibrium separation distances from the surface because this lesser overlap resulted in a relatively lower adhesive force relative to the colloids that had greater overlap. So what I'm going to do now is take the results and run them in detachment mode. And so what we need to do is load the flux.at file that we obtained during this run. And those were obtained here in this output Happel load. And so the flux.at, I want to make sure that that's correct. Yeah, and one thing I should show you is this is the default directory that was chosen. I could have changed it, but the default directory that the output files were put into. So there's a flux.at file, a flux.x file, and a flux.rem file. And those are files that contain the population of particles that either attached, exited, or remained without attachment, or were provisionally attached in the remaining file. And so we're going to load both the attached and the remaining. Also, if you want to look at trajectories, all the attached trajectories, exits, and remaining trajectories are there. Now, we create files for all possibilities, but the ones that are greater than 2 kilobytes are the ones that have significant information. So, Traj Hap 1 through 4, all those have significant sizes because all 4 particles attached. If one had not attached, say particle 4 had not attached, but instead exited, then this EX4 would have been populated with significant information. And these are easily put into Excel using the text wizard and in Excel, and then can be manipulated to make additional plots. They're also fed into the upscaling algorithm, as I'll describe in a different video. So we're going to load the attached here. It's now reading that file in. Now we can load the remaining, in case there are some that are remaining without attachment, which in this case I believe there are. Remaining. And once those are let in, okay, so no slow motion colloids are in the rem flux file, and that's because they all either provisionally attached or outright attached. And now we can set the output directory. I'm just going to let it go with the default. And we can run a perturbation. Now, if I keep all this parameters the same, nothing will happen because there's no perturbation. But if I, for instance, increase the fluid velocity by a factor of, say, 4, a factor of 100, 2 orders of magnitude, so make that 10 to the minus 4. Let's see if that has an effect. So I've done that. Going to run the perturbation simulation. It will open up a dashboard just like it does during attachment, but what it's going to do is show whether or not this thing starts rolling in motion. And what you see is, in fact, that the separation distance is getting even lower while it rolls. Only very, very slightly, though, and that's, I assume, because of the greater normal force from the increased fluid drag, right? There's a normal component still at that location on the collector. And so it's driving it a little closer into the surface, but this thing seems to be rolling along. It's going to do it so very slowly, but you can see that the trajectory on the collector is not just a point now. It's becoming a arc. And I don't know how far it might roll. And we don't want to watch it all day, by the way. So hopefully this thing will exit, end up moving away from this very close separation distance and go into solution. Like, for example, the separation distance is now starting to increase slightly. Also, the contact forces now are in equilibrium. The blue and the red are over each other, but they're both starting to decrease as it moves away from the surface a bit. The area of the zone of interaction covered by heterodomains is decreasing. It's rolling off the heterodomain. So that is what's driving its separation from the surface, lesser normal attraction force. So it is rolling off the edge of this heterodomain. Okay, so the fraction of the the zone of interaction occupied by heterodomain is approaching now just 80%. And with that, the separation distance has increased. Now look at these numbers, right? We're talking about 0.1, maybe going up to 0.2 times 10 to the minus 9th meters, which is 2 angstroms. So it has moved away from the surface 2 angstroms. But of course, as it starts to move away from this surface and off of this heterodomain, the separation distance will increase dramatically as the fraction of the zone of interaction occupied by heterodomain decreases. So it's worth watching this, even though it's a bit tedious. But the contact forces have now dropped below a nanonewton. And so this thing is starting to lose its contact with the surface. What we don't have plotted here is the contact area, but that is also decreasing as the contact forces decrease. In other words, the deformation of the colloid is decreasing. And this will become especially important as the area of the zone of interaction drops below somewhere around 50%. Because, and of course it depends on the ionic strength and other factors, but there has to be some threshold, otherwise the interaction becomes net repulsive. And so there'll be a dramatic change here very soon. So now the colloid is a good 4 nanometers away from the surface, nearly, quite close to. And the area of the ZOI occupied by heterodomains is now getting quite close to the threshold where the interaction will become repulsive. And you might ask, why does the colloidal force show repulsive? And that's because, of course, that it is snug up against the repulsive forces in terms of Born and steric. You can't see that exponent here, but it's going to be some small, 10 to the minus 11th Newton, right? So basically 40 piconewtons. Okay, so something should give way here very soon as this area occupied by heterodomains reaches down towards 0.4. Because this is a 20 millimolar ionic strength, it's going to allow a somewhat lower threshold, like around 0.4. And you can see that the trajectory is still quite small over which this has happened as it's releasing from the surface. Okay, so now the colloidal forces are becoming quite significant in terms of the repulsive forces were so it's confusing, and I got to explain to you what happened here. For a moment there, the forces were repulsive and it went into the secondary minimum, but then it got over another heterodomain. So it moved immediately over another heterodomain, so it's skipping like a rock across heterodomains. So the area of the zone of influence that's occupied by this new heterodomain is approximately 0.7, 70%, and now the separation distance is dropping back down to a few nanometers. And so this colloid is finding other heterodomains to attach to because of the high surface coverage by heterodomains. And the question would be,
whether or not it'll find header domains all the way along this arc, or whether the tangential velocity will become so strong that it cannot reestablish contact in response to that tangential fluid drag. So what I'll do is let this run for a bit and come back to it. Okay, well, this colloid has now progressed across the second heterodomain, and notice that it went through a maximum fraction of the ZOI encompassed or covered by heterodomain, and about 0.9, and it was less than this previous heterodomain because the colloid did not go as close to the center of that heterodomain, and so it couldn't fill as large a fraction. And as it comes off of this heterodomain, it will skip and probably find yet another one. And notice that these two heterodomain encounters have all occurred here in this little stretch of trajectory. Notice that the drag force is relatively constant across those two heterodomains, whereas the colloid velocity, though, shows variation because of the interaction with the heterodomain, right? The drag force emanates from the fluid interacting on the colloid, but the colloid velocity interacts or results from not just the drag force, but also the colloidal interaction forces. So momentarily, we should see this colloid come off of contact with this heterodomain, go back into the near surface, and then presumably find another heterodomain. And this could go on for a long, long time. So I won't continue showing the video after the next step. But let's just see what happens at this step. And sure enough, same thing again. Okay, so brief interlude in the near surface shown by the magenta dot up here. And now back into contact with, again, the tangential and normal drag forces staying relatively constant. The tangential is increasing slightly as it makes its way across this arc, but still got a long ways to go. And obviously we don't want to keep watching this forever. But you get the idea. This thing would continue rolling. If it had a lesser surface coverage by heterodomains, remember this one is 50% coverage, so they're quite frequent. If it had a far lower frequency, like the values we back out for glass beads are somewhere around 0.01%, right? Much, much smaller prevalence of heterodomains. And so it would be very, very different. It would skip and very possibly, in fact, not encounter other heterodomains because they may not be directly in the path. So this is a behavior under high surface coverage by heterodomains. The point is, though, that this colloid is being mobilized. And whether it ultimately, in the simulations, ends up in the bulk fluid or not, I can't say without running this further, but it could be a long time in running. My guess is that it will, because the tangential drag will continue to increase and push it along, and eventually, when it gets to the near surface, it will get farther out into the near surface. Notice that this one, the separation distance it achieved was somewhere just above 7, and then somewhat higher here on the left top panel, but that would continue to increase as this thing moved into greater and greater tangential drags. And so I think it's very likely, left to its own simulation here, it would end up detaching and likely exiting. So what I'm doing now is I have loaded that set of data in again for loading, and now I'm changing the ionic strength down to 1 millimolar, as we would do in an ionic strength flush, and perturbation, increase or decrease the zeta potentials down to negative 65 millivolts. I'm going to hit that heterodomain radius, and I'm gonna not change anything. This should still be 0.5, but we want to make this now 65.
And I don't know if I want to speed up the fluid velocity or not, just to make it run faster. Maybe just speed it up at least an order of magnitude. That wouldn't mobilize them, but it will help things move along. And so we've got that. I think that's ready for running. So I'm going to use the same default output directory, and now we'll let it go with the 1 millimolar ionic string flush and stronger negative zeta potentials, or stronger positive zeta potential on the header domain. And so this could take a while, but the point is that the colloid initially, this one attached with about a little more than 50% of the zone of interaction occupied by header domain. The reduced ionic strength did not detach this colloid, it reattached. It reattached at a somewhat greater separation distance, moving from 3.708 out to 3.73 something. So just a slight increase in a fraction of an angstrom in the separation distance. Okay, so second colloid dashboard. Okay, so its separation distance has increased to about 4 nanometers, still mobile, but now has reattached. And so the zone of influence was occupied by about 50% by the header domain, and it has reattached. So in contrast, the third particle, which started with a somewhat smaller area of the ZOI occupied by header domains down at 0.4, ended up going from contact into the secondary minimum quite rapidly. The fluid velocity here is not very high, so it could take a while. The point is this thing is now mobile. It hasn't reattached. Now, it could easily find another header domain with this high header domain frequency. The time steps are also quite small, so it must be using contact time steps for the simulations, right? Because if it's passed so far, it's a tenth of a second. And so separation distance is now increasing to significantly larger numbers. We're up at now coming up to 80 nanometers from the surface, so it's getting significantly far away. And it could potentially get swept away. So the point is that you can visualize what's going on through the GUI, but with the way you'd run this for a large number of particles, of course, is in parallel and not looking at these real-time figures because they slow things down too. But it's a good training process, and that's mainly what this GUI can be used for. You can see that the particle has come over another header domain and is now getting increased area of the ZOI occupied by the header domain. Separation distance is kind of plateauing, and probably as the area occupied by header domains increases, it'll start pulling the colloid back towards the surface where it might reattach. The point is that you can mobilize them through ionic strength reduction as well. Notably, the work that Anna Rasmussen did in Rasmussen 2019, as well as Kurt Van Ness in Van Ness et al. 2019, they showed that the flow tended to mobilize the larger colloids and did so more significantly than the ionic strength reduction did. You can barely see the one contact point that was reported before it went up into the secondary minimum. And it's been moving in the secondary minimum slowly. So it's moving along the surface here. It could reattach if it finds another header domain. But because there's two interesting things here in this trajectory. One is it's bouncing around up here at distances between It's 20 nanometers, 30, 40, 50, around 60 nanometers, between 50 and 70 nanometers, and more around 70. And that's because the secondary minimum has shifted outwards to that distance because of the low ionic strength and the increased range of the electric double layer repulsion. The second feature that results from being so relatively far away from the surface, around 70 nanometers, is that the projection of the zone of interaction, the zone of interaction over the collector, captures not only more heterodomains, but also more non-heterodomain occupied collector surface. And so the zone of interaction occupied by heterodomains bounces around as it moves around over that surface, but the maximum is now somewhere around 0.5, 0.55. And so, so this being higher off the deck causes the zone of interaction encompassed by heterodomains to be reduced. The maximum is now around 0.55. And so even with 0.55 fractional coverage of the zone of interaction, we do not see a rest because at this point, at the 1 millimolar ionic strength, that does not constitute a large enough zone of interaction coverage to allow net attractive interaction and therefore a rest. And so those are the primary attributes, and so you can see that we have mobilized this colloid. It's moving slowly. At the scale of a pore, it's mobile. At the scale of a packed column, it would not elute necessarily and would be retained without attachment. It's these slow-moving colloids that may well produce the extended tailing during elution that we see in packed porous media. So as always, please ask us if you have any questions. We hope you enjoyed this presentation of the 40% mobilization. You can reach us by email, william.johnson@utah.edu. Both Eddie and I will be in the loop and look forward to hearing from you.